And these are the general formula. Now you can work out a simple case like now work on a circular cavity. Basically, the cross section now is just a circle, so it could be specific. We set the radius as d. Not d. R. The length is d. The radius is r. Capital R. Okay, we want to solve the wave more inside. Okay, this is just an example. You can also have other kinds of cavity. The one thing you can obviously solve is the rectangular cavity. So basically now becomes a cubic or rectangular cube. Right. In a rectangular cube, you can call whichever is the z direction is up to you, because it's just symmetric. You can call this is a z direction or the other is a z direction. Doesn't matter. You can still use the same formula, except that once you choose where is your z direction, you choose that component as your psi, or the psi is proportional to that component. So, but equivalent, you can solve the rectangular cavity this way. But for circular cavity, obviously the z direction is different from the perpendicular direction. Is set already set the z direction. So the perpendicular wave equation, this one, you can solve that just like what we did for the Laplace equation, right? Because we already have the equation for the Laplace equation, or the solution for the Laplace equation, subjection. Yeah, it's 8, injection is 8.80. 8.80. 80. Okay. So this equation is for both cases, for both the TE mode and TM mode. You're solving the same equation. So the same solution applied. So in this case, psi depends on x and y, but then we can change it to polar coordinate, so it becomes the radial coordinate, and then as you move angle, so basically set whatever your x and y, you set this is your polar from the center is your polar coordinate, and you have as you move angle from the x-axis. We have already solved that before. So it will be given by Bessel function. I mean, in general, it's a sum over Bessel function. But for one more, write sum if you want. So sum over m from 0 to infinity. You can have some coefficient, just as e sub 0, but it can depend on m. Then you have a j sub m. And now it will have some radial wave number. This is gamma mn times rho. E to the I m phi. And I mean, originally you take m is from minus infinity into infinity, but if you impose m is positive or 0, because you usually talk about Bessel function with a positive order, the negative order actually is proportional to the positive order. So you can combine the m minus m to this one, but then in that case, this factor can be plus or minus. So it doesn't matter actually. It's just the phase factor is different. The resonant frequency is the same. Okay, then this is a solution of that, because you substitute this to the transverse Laplacian. You see that that will give you the gamma squared that you want out. Because you're not familiar, you can go back to what we talked about, Bessel equation, Bessel function. That should be somewhere in chapter 3. If you're not convinced, then I can look it up for you. See which equation is better. Actually, you probably need to start from section 3.7. Start from the Laplacian in 3D in symmetrical coordinate. Except that the transverse part you don't have the partial square, partial c square, so you keep up only the rho derivative and the phi derivative. So only the first three terms in 3.71, and then you go through the same derivative. So then the transfer Laplacian is this one, and then you have this m square term by the phi derivative, because you have partial square, partial phi square divided by rho square, and partial square, partial phi square or minus m square, right? That is given by that one. So the Bessel function will satisfy the equation 3.75. The Bessel equation d squared d rho square plus 1 over rho square. Actually, the 1 over rho d rho, and then you have the k square. K in our case is gamma. The gamma square minus m square over rho square. And that operates on this Jm gamma rho. That is 0. Okay. And so this is the Bessel equation. Compare this with that one. So that actually is satisfied by this Jm. Right. And this gamma square is coming from this term for this equation, but gamma square in this Laplace equation is coming from the c derivative, but we don't have the c derivative. Basically, this is like coming from the c derivative. So you have gamma square, but the equation is the same. Okay, so this is why this is a solution for this one with the same. So gamma equal to gamma sub n. Okay, and now we want to impose the boundary condition. Okay, to impose the boundary condition depends on the case. For the TE mode, psi is 0 at I mean, if we always impose that, actually, I should say the psi for the TM mode, psi is 0 on the surface, on the side surface, which is TM mode. The boundary condition is on the surface is rho equals to rho. Psi is 0. So you want the Bessel function to be all 0 on the surface. So it means that say m gamma m rho equals to 0. Actually, rho is r. It means that gamma m n times r is equals to what we define as the xmn. Those are the roots of the Bessel function j sub m. Okay, we consider that in chapter 3 already. We have a table in chapter 3 about the root, the zeros of special function. All these zeros are given. I mean, not all. It's the first few zero of this JMN. JM is given in chapter 3. So gamma MN, so gamma sub MN is equals to XM. So these are considered known values. You can look that up, or you can use a computer program to solve that. And once you have this gamma MN, you put it in here. So it means that omega, that the Western frequency depends on M, N, and P, because lambda is just given by M, N. The square is equals to epsilon. Now this gamma MN, which is like you can change the XMN square, R square, plus pi t. That will give you all the MNP omega. And now for the lowest mode, for this is TM mode. TM mode P can be 0. Lowest mode, obviously you want P to be 0. And then you find the smallest XMN, which quite often is from M equals 0, but we can look that up in chapter 3. There's a table or below 3.92. So the smallest one is M is 0. And then the N you can usually count from 1, the first root and the second root. So the lowest one is x01. X01 is 2.405 something. Right. That's a TM. That's the TM mode, but we need to consider TE mode also. For TE mode, some spacing. For TE mode, it's just similar. And the TE mode, the requirement is that the partial psi partial n on the surface is 0, and n is just the row direction. So you require partial rho Jm is gamma Mn. Rho is 0. Okay, and this means that gamma Mn rho is equal to, now it's not, instead xmn, it becomes x pi mn. Pi is just a notation. It means that Jm pi, the derivative of J sub m with respect to the argument, and evaluate at these values will be 0. These are the roots of the derivative of J sub m. Okay, and the table is a little bit. Is in this section 8.7 is below 8.82. You have a list of that x sub mn. In this case, the lowest mode actually turns out not at m equals 0. And then this is TE mode. So TE mode, so you have P, but P is not 0, and so for the consideration here, so omega MNP square is that becomes x pi mn of r square t square. Okay, so the lowest p is actually 1. So you must have a 1 here, so you cannot drop this term. But then the lowest xmn is by the table is actually given by x1n 11 pi. Is given by 1.841. Okay, and this is for the first zero of j sub 1 pi, right? The reason is that you just qualitative part j sub 0 and j sub 1 as a function of argument x. The j sub 0 x, j sub 0 start from x equals 0 start from 1. So j sub 0 is like that, it's drop, and then it's oscillate, but the magnitude also decrease, so it keep decreasing, something like that, right? This is j sub 0. Okay, so the first zero, not counting this at x equals 0. The first zero is of a zero. This is when x0 is 0. So this is x01. But x0 pi, x01 pi is when x0 pi is 0. So the first one is actually at this one. So this is x01 pi. Right. When the derivative is 0, so this is 0, this is 0, right? But x sub 1 is, and j sub 1 is something start from 0 actually. So j sub 1 start from 0 and then go to go back to 0 somewhere between these two 0. They have some of these properties, something like that. Okay, so for j sub 1, the first 0 actually is larger than a sub 0, so this is this is x11. This one is larger than x01, so that's fine. But the first value when the j1, the derivative of j1 is actually smaller than this one. We actually turn around at a point smaller than this one, smaller than this. So this is x pi 11. X pi 11 has a value smaller than x pi 01. Okay, so that's just a property of a Bessel function. So actually, it turns out that this is smallest, but then the smallest frequency would be omega 111. That equals to 1 epsilon and x11 pi square over r square, and then plus pi over d squared. At least p is 1. Okay, so that would be the TMO, right? But obviously, you compare this one with this one. Compare this one with this one. Which one is smaller than the? Obviously, this one is still smaller than this one. But then you have the extra term here for 0, 1. So omega 0, 1. That you can take 0. It's just x01 square r square. Whether this one is smaller than that one. Now it depends on what d is, right? If d is really large, then it could be this one will be smaller than this one because of this value actually smaller than this one. Right, so it becomes slightly complicated, right? Okay, but that's how you calculate all the mode using Bessel function and all that. It's okay. So and this is just the z component, and once you have the z component, you go back to the calculate the transverse component. But the transverse component is given by 8.76 and 8.77, and that is slightly different from the waveguide, because waveguide has a K. Now we are not using K anymore because you are using sine and cosine. So basically, you go back to 8.23 and 8.24. So all the puzzle C depends on what uh, you have TEMO or TMO. TEMO sign has this sign. I mean, XG has this sign, and sine terms. For TMO, EZ has the cosine term. So if you use like a partial C, will give you the same sign as this one. So ET will have the same for the TM mode. ET will have the same sign of this sine function, right? Because I mean that this is TM easy, and I don't know what it was. I'm just out of time. To get to divide the equation 8. I'm just pointing out 8.76 and 77, 76 and 77 are derived from 8.23 to 25, right? And the only difference is that we are not setting puzzle C to IK to solve that, because now there's no IK. You are using sine and cosine, cosine K and sine KC. And so you just change that to either. So ET and HT will propose the sine and cosine according to this equation, and then once you figure that out, the rest is similar to what we had in the waveguide. So the only complication is that the the transverse T and ET, transfer electric field, transfer magnetic field, they all have this either sine or cosine according to this equation. Okay, and then you can derive 8.76 and 77, which is straightforward. It's similar to what we did for waveguide. And then you can have, once you solve for psi given by the Bessel function for the circular waveguide, for circular resonate Bessel function, and take or whatever the transverse derivative that you need, and you can get the transverse electric field and magnetic field. Okay, and that will give you the full field structure of the mole. Okay, but that is straightforward. And okay, that's the end of 8.7.